We're going to talk about the workflow of the additive manufacturing process. As it says there, I am Kyle Bates-Green, a subject matter expert at Edmonds Community College for the TEAM grant and Matt EDU grants. I have a slide at the end. You can reach me at kyle.bates_green at edcc.edu. I'm also the education programs coordinator for the Institute of Flight in Mukilteo, where we do a lot of makerspace workshops on topics like this. So you can reach me there as well. So what I'm going to go over is all going to be themed around this slide here, really, about the FDM workflow. So for those of us who don't have experience with all the acronyms already, who haven't read maybe the ASTM standards, the FDM workflow, fused deposition modeling, is a type of 3D printing, which basically just means where we are taking material that can flow and putting it into place and then solidifying it. So that mostly means thermoplasts, in which you've seen MakerBots, most consumer-grade 3D printers are doing FDM, where they're melting a plastic and squirting it into place and cooling it as quickly as possible, obviously, because you want the liquid to stop flowing and become a solid and stay where you put it, but be hot enough to fuse to the previous layer and be structural. There are lots of other ways to do that. You don't have to do it with plastics. You can do it with anything else that can flow and solidify. So anything that is even solidified once, so like a thermoset or something like a photopolymer that sets in place. You can put the resin in place and then shine your UV light on it to get it to cure. You can take powders and fuse them into place with a spot sintering laser, or you can glue them into place and then put them in a furnace after you're done with your part and burn out the binder afterwards. You can start with a supersaturated solution where the solvent evaporates off so fast that your precipitate is crystallizing in place to attach to the previous layer. There are lots of things you can do. But basically the process currently for additive manufacturing is that you're adding layers together. And FDM, of course, is heavily biased towards always adding a layer on top and never returning to a previous layer. We'll see a few of the consequences of that, because there are positive and negative consequences to using that method. But basically, we're going to start in the top left-hand corner here with design. So you had some idea and you're working on making a design. Maybe it's a test, maybe it's an exercise, maybe you have scanned in data, maybe you even have been working with Mathematica or Maple, and you have generated mathematically a parametric surface that gives you data that you can give to your programs to tell them where the surface is at any given height. So that data, that geometric data, is going to you're going to put that into what's called the STL format. So at the top, that format, the file format, we have STL file, standard tessellation language, or standard triangle language, or stereolithography files. It's kind of a backronym. So all those things are the same thing. STL file is the real name. And basically what it is any surface you can imagine can be made up of a number of triangles, which is the simplest two-dimensional shape you can make, all stacked or all connected edge to edge. That also, however, means that you can't have an actual curved surface. So nothing can be a true curve. Nothing can actually be a circle. Just like in the universe, nothing can be a true circle, because a circle has to have an infinite number of points around it and no sides in order to actually be a curve. And there aren't an infinite number of particles in the universe, and there certainly isn't an infinite amount of memory in our computers to remember an infinite amount of facets. So there are limits, but as we're telling our printer to move the print head, it'll make a convincing curve as long as we have made that file correctly. So in that design step, there's a lot of software you can use to produce these STLs. Some of it is free, some of it is very reliable, some of it is very high priced, some of it is very powerful, some of it is suited to different methods. But the basic things you're going to do are drafting, where you start from a two-dimensional surface and you pull it up and make modifications, or sculpting, where you start with a mass and you work a little bit less accurately, but you kind of tell the computer where you want to push in and pull out mass, and it simulates the behavior of that material. And then, of course, we also have that mathematical generation from an equation, or scanning in things. Once we've got the STL file, we're going to slice it into layers, which means we have another piece of software that we pass that file to, and it takes that piece and separates it into Z-height layers. That's the current state of the technology. We may have more powerful things in the future that can decide that different parts of it need to be built in different directions and stuck together by one contiguous process instead of an assembly process. Remember, we're not doing assembly here. We're fusing things on continuously. But right now, all we're going to do is take those shapes and say, if I decide each layer of plastic I'm going to squirt on top is going to be 1/5 of a millimeter thick, then I'm going to have 0.2 millimeters in my slicing program is going to separate my shape into 0.2 millimeter cross sections. And each cross section is then going to be planned as an outline that the printer draws out of plastic, and then it's going to draw some lines across to stitch them together, depending on the infill algorithm that I've made. Now that algorithm, and I'm going to start moving forward for some of the pictures of that. The algorithm for that is not going to decide for me, how dense it's going to be. I'm going to give it instructions. So let's say we're talking about the CAD stage right here. You can see we have this curved surface cut into this square, this cuboid shape. And that curved surface, if you take a careful look at it, is actually made out of facets. This is dimensioned at this point. It's got millimeters, etc. You can bring it in different ways. And here's the STL file that I was talking about, where now it's made out of facets. And if I give that a finer curve, then it's going to be more facets on that curve you see right there. But of course, that means a bigger data file and more processing time, etc. And there are points at which that can become prohibitively large. What you see on the right-hand side there is what is inside of an STL file. If you know how to read it, how to crack it open, or reverse it out of binary, you can read this. That you can encode them in text as well. And all this is, you see each surface has a normal direction, which is a vector that tells it which way is out. That's going to make it easy for the next step where the slicer needs to decide where the plastic goes on the inside. This is going to tell it which direction is inward and which direction is outward. And then each of those blocks of numbers you see underneath that initial vector of 3 numbers is a block of 9 numbers, which you may notice is 3 times 3, 3 points in space, X, Y, Z, and 3 points is enough to make a triangle, and they're all triangles. So each block of code, then now you know what all those parts are, and now it's just lots of those little blocks. Millions and millions and millions of them in some cases, but this one's not too complex. Oh yeah, and this STL file has no scale on it, so it's arbitrary units. So if I export from if I'm designing my CAD program in millimeters, and then I bring this into my slicer. And my slicer is used to using inches, then now I've changed my object, right? So you've got to get your standards correct there. You got to communicate with your client correctly so that you know what systems you're using. There are other ways to encode this information, and some of them are basically STL files wrapped in preferences that keep track of those settings. Okay. Slicing software, this step right here. Here you see the geometry that's been brought in. We can choose our temperatures that we're running at because we have looked at what plastic we're using and we know how much we want it to flow before we freeze it. We can decide on the speed that the head moves. If it's not jumping across open spaces, then I can move it pretty quickly. But if it is going to be stopping and moving across an empty space where it needs to not extrude, then I need to slow down and pause at that place for a moment so that I'm not leaking plastic and leaving behind a bead, just like a hot glue gun would, when I'm moving across that empty space with those long threads that they create, because it can't perfectly stop extruding just because it stopped turning the gear. There's still hot plastic in there, in that reservoir right above the tip that's kind of leaking out. There are lots of other options in there. You can get into that and play with those anytime you want. So here's what those tool paths look like. And one of those 0.2 millimeter cross sections that I'm talking about in the case of the settings we have right here is what's highlighted in the middle of this green shape you see in front of you, where the tool head in this case, the extruder tip, is going to move around and draw that outline of the shape first. which is just one cross section of the shape, and then it's going to stitch it together with that rectilinear path you see inside there. Now, if you're interested in complicated infills that maybe are stronger in 3 dimensions instead of being, because if you imagine all these layers stacked on top of each other, they're all, it's like a bunch of hollow diamond or hollow square pillars, right? If you want something that's really strong or isomorphic, has isomorphic properties in all directions, same properties in all directions, then you might try looking up Disney Zurich on YouTube, Zurich, the city. Disney has a research division in Zurich. Some other people do interesting stuff with this too, but Disney puts YouTube videos out about it. Where they have written some cool equations for 3-dimensional infills so that the algorithm fills in this space with shapes that are stronger in multiple directions, as opposed to, if you think about the shape we have in front of us right here, if I were to take a wood chisel to it, there's one direction where it would be really easy to cut between the layers, and other places where it would be harder. So the properties are different in different directions, and that's one of the consequences we'll talk about with additive manufacturing too. In the time we have remaining. All right, Gcode, it's basically the instructions, XYZ instructions to go places, turn the gear to pull in plastic at a certain rate, make sure the temperature is the same. Pulling in plastic pushes out the melted plastic that the solid plastic is pushing into. And it tells you what speeds to move the head at in different places, when to do those pauses we're talking about, etc. All right, so the advantage we have it for additive manufacturing. I'm going to run backwards really quickly. So that gets us to a place where we've got the tool paths generated. We're printing our objects. Now, at inspection, this is critical. This is just like the engineering design process in anything else you do, where when you print it, the point is that you can go back to a previous step and discover what didn't work correctly. So you're going to be doing your quality control, or you're going to be doing your testing or whatever, and you're going to find that your surface resolution needs to be finer, or your resolution needs to be finer in a specific place to get it to fit into something that you, the way you want it to. And that may mean that the software you're using isn't sufficient for getting the shape that you want generated, even though the hardware you have can make it. So you're going to run into all sorts of complicated things in here, especially with the current state of the technology, where things are changing and improving all the time, where you can change your part to get what you actually want in the end. And you may be, some of this may involve, jury rigging, skipping some parts in the process, of course, especially if you're working with consumer grade materials like I do in my open makerspace most of the time. More complicated systems, you're looking at a range from, for 3D printing, from $300 to $300,000 on machines we're talking about right here. So depending on your specific application, you may have a machine that you can't mess with the settings in it, right? Because that machine is there to protect itself from the user, because it knows what it's doing. The people that built it will tell you exactly what it can do. Or you may have a kit you built at home that you can make a lot of changes to. Once you've got that G-code, you print, concept, redesign, you get the idea, etc. So, okay, so advantage for additive manufacturing. You can make these complex geometries because you're building up one layer at a time. So you can leave hollow spaces. We're going to look at some examples of that real quick. You make short-run parts are the highest advantage for additive manufacturing right now. Additive manufacturing is probably never going to be cheaper than forging or injection molding for just making mass parts, especially quickly. But it makes cheaper short-run parts. So imagine I've got a part that I want to make by injection molding, and it's something that fits in the palm of my hand. If I want to make a mold for this, I'm sinking maybe $20,000 to make an accurate mold to make this thing, and then I've made the thing, and maybe I discover that it's actually not quite what I want when I test it, right? 3D printing is going to make that for me, for 12 bucks, something like that. If I do the injection molding, then if I'm making more than 400 of them, if I'm making thousands of them, then suddenly my price per unit starts to drop down to cents, right? And now additive manufacturing is 10 times as expensive. But for a single part, for short runs, additive manufacturing is going to be hundreds to thousands of times cheaper than starting up a mass production process, which means what are the short run processes we can think of? Prototyping. We're making one part, testing it, then changing it, making it, testing it, changing it, making it, testing it. I can do that prototyping I can do that prototyping cycle with a small part 5 times today. Whereas if I want to get that, if I want to, get it similar to mass production quality without 3D printing, I'm going to be mailing it back and forth to a machine shop or getting in line downstairs with the machine shop that I have in-house, and we're talking about a months-long process. So it's saving us, not only thousands of dollars worth of material cost in this point, but of course, you don't want your engineers sitting around waiting for these things to come back because you're paying the salary, et cetera. And if you're working on a startup, man, you'd rather have this agile process than, waiting for another company that you're contracting with to get those parts back to you. Tooling, also short-run parts. If I'm working in the Boeing factory near where I work at the Institute of Flight, I may discover that I just need 20 of these parts that are a guide to help the technician get the screw, get the rivet positioned correctly. And if I don't have that position correctly, I've got a 20% failure rate on that rivet, and I don't want to ruin that panel. Right? But that tooling, it may cost me $120 per piece to 3D print that one piece of plastic that helps me fit it correctly in there every time, but it's worth it for my process, right? Or mass custom, where we've got these parts where each person needs a slightly different one, right? If I'm selling in my mall boutique nameplates where you can choose your own patterns and stuff, I can't make a different mold for that each time, but I can 3D print it. So slightly different things, iterations where the customer can make quick changes and quick decisions. Now you've got mass custom production. All right, and the last one is logistics, which is the distribution of production, right? So if, let's say those mass-produced parts are cheaper and they're reliable, but I don't want to have a warehouse at every one of my work sites that's ready to, store 5 of each part that might fail. So instead what I'm going to have is a 3D printer with the material that I need and the files loaded up on it. Imagine the extreme case of that. If I'm flying to Mars, instead of bringing 5 tons of replacement parts, when I know my statistical model predicts, if I want to be sure, I've got to carry 3 of each one of those parts, but I could carry, but I know there's a certain limit to how much I'm going to end up using, right? But if I could instead carry 20 kilos of printing plastic in a printer, that's going to save me a lot of mass, which especially if I'm going someplace where, you can't get Amazon shipping for that part to Mars. If your resupply is 5 years from now, then you'd rather be able to produce the stuff, especially if your 3D printer is a gantry that you can set up that where you're combining materials where half of your filler material is Martian regolith, right, or whatever sandy material they have there, then I'm printing ceramic parts out of basically silica material that I find, that I'm scooping up and sifting from the ground. So now you've got a resistant, now you've got really a solution, a process solution, rather than a supply chain problem. Okay. I'm going to skip over the hardware limitations a little bit because I'm going to talk about those, and we'll really want to get onto those pictures and not use up all our time. But basically, think about all the problems you can have with a hot glue gun. You can have them with this kind of 3D printer, and think about all the problems you can have with getting powders into place. You can have those with other kinds of 3D printers, etc. Everything in here, just like everything in engineering, everything is a trade-off. So if you attach it more strongly to the plate so that it doesn't come out of place while it's printing, well, now you're more likely to damage it when you try to get it off the plate later. If you want finer edges, you're multiplying the time it takes to make thinner layers, right? Because if I've got layers that are twice as thin, now that's twice as many layers for me to print. And of course, there are all the limitations of materials that you can use for this process because it needs to be able to flow into place. All right, so here we've got some examples where we can show one of these advantages of variable bulk properties. These 2 pieces right here have a hexagonal infill where they have some hollow space inside of them, but they're different. The one on the left is 8% solid internally. The one on the right is 24% solid internally, as I recall. So that means I have a printer, one fabrication device, that with no tooling changeover, no post-processing, no technician time, has produced two externally identical parts of the same volume with a different mass, a different density as a result, and a different strength in bending. So these have different moduli, right? So one is more flexible than the other because it has less internal structure, and one is stronger than the other. One is stronger in, let's say, yield stress because it has more internal structure. And this took no work from me to change these properties, despite the fact that they have the same net shape and the same volume. Okay, here's another view of that internal structure right there. You can see some infill. This is the simplest infill that you can make. It's a set of lines going one direction, one layer, set of lines going in the other direction. But this also lets you see kind of that method that we're talking about, where the outer layer, we want to be non-porous, we want to be solid, we want to be strong, but that infill is just there to share stress from side to side. If you've done your mechanical engineering courses, you know the point is that you can transfer stress around that structure you're making, and the infill is just there to do that. So the infill is mostly bearing tension, and the shell is dealing with impact stress and compression. All right. These are shapes that are very easy for additive manufacturing right here. There's no infill. If you look at them, at no point in their height does the tip ever have to pick up and move across empty space. There's nothing weird and complicated for it to do. It's just going to keep moving and just making those shells. And that lets you make actually pretty rigid, especially if they're corrugated, like what you see right here, pretty rigid structures. But if you reduce the corrugations or if you use a softer material, now you get a really flexible shape. So these are easy and fast to print. So you do kind of want to think about the type of shape that's suitable to additive manufacturing. Here's another one that's not easy for additive manufacturing, but is extremely difficult for non-additive manufacturing. If you take a look at this, you can see kind of a snaky up-down hollow chamber inside of it, and lots of little dots on the surface. Those dots are pores. This is a model of a GM compression blade. This one's a combustion blade fin. And basically the point here is that if I want to make this shape where gases can flow through it in the way I want with these complicated hollow internal chambers by machining it, I've got a real task on my hands. And it's going to cost me a lot of money. Some of that's impossible. Some of it needs to be done with weird bits of ceramic in the casting mold that you then chemically dissolve out later. Lots of post-processing, lots of problems for quality control. But if I can additively manufacture this, I just leave hollow space where I want there to be hollow space. I just don't fill it in. I don't have to remove anything afterwards. There's no complicated steps for human hands to mess up. There's no process series of steps where one of them goes wrong and it ruins quality control for everything else. I just make the part. All right, here's another kind of example of that. I can leave hollow space, so that means we have this mid-processing process, this kind of new concept of mid-processing right here, where if I'm manufacturing something, I can now drop things, I can drop other parts inside of it where I've left hollow space that the tip's never going to travel over. And now those parts are fused. I can have moving parts of multi-materials dropped inside each other if I'm giving my slicer information that tells the tip never to cross over the space where I'm going to put the other parts. And these parts are now integral, right? These are now part of the shape. No matter how I shake these shapes in front of me, those pennies can never fall out because the last layers were finished fusing on top in one continuous additive process. Here's another one. Build plate orientation matters. This is more about limitation than anything else. The piece you see before you was printed in this orientation, but also screwed closed as a scissors left. Yes, it was printed as a single printed part, and I can take that and I can turn the knob on top and screw it all the way open or screw it all the way closed. It's a scissors left, just a scissor jack like you've seen before. Because when that is closed, all the individual moving parts touch the ground and are therefore supported and stuck, and can have the next layer set on top of them and never have to touch each other. So nothing is fused together. They're all independent shapes. They're all trapped inside of each other. No matter how I orient this, I have to break it for those parts to come apart. But I don't print it with those big convenient flat sides face down. Because if I do that, then some of the parts don't touch the ground. So the orientation I'm printing in is also part of my printing parameters. it's not okay for me to just send my geometry to someone and say, print this, because it may have to be printed in a certain direction. Or, you know, there are maybe other settings, of course, that matter very much as well. Okay, so these are also moving parts. They're not assembled. They're printed in one piece. If you look at the helical gears on the right, then you can see that they have a little rim on the inside of the planet gears that notches into the rim, the inward notch of the sun gear in the center, and the ring gear on the outside has a notch outward to itself, so that those pieces are all trapped together once they're printed. Don't need to touch while they're printing. It's one moving part. So you can imagine I could make completely fully enclosed gearboxes this way, and has been done. You're going to have trouble getting in there to do repairs, but I can print them as one piece. And then the piece on the left, of course, is a set of cylindrical gears as well. So you can start thinking about complex parts you can make here. And here's the one that's most exciting to me. My background was originally in material science. We're just about out of time, so I'll stop in just a moment. We'll wrap it up. And you can see that what we have there in the center is an accordion joint. This is printed out of two materials, polylactic acid, and there's a polyurethane blend in the middle that's pseudo-elastomeric at room temperature. So if you think about the kind of robotic grippers or prosthetics that I can make with these integral flexible components, where part of it's flexible, part of it's solid, there's no assembly process, I can make it at home on my 3D printer, so I can make my own prosthetics that's customized to me. I can print it anytime I want, so the supply chain problem is solved. And I can put these interesting, whatever kind of flexible shape I want in there, I can put in. Sorry if you're catching it in my background noise. Mass reduction, if you look up genetic algorithms, they can cut away material. Those commonly make bird bone type shapes that nothing else can manufacture, whereas additive manufacturing can. These are some ways we can take in lots of data. These are just made with different CAD software. The model of the United States there is just US Geological Survey data pulled in. So you can pull data from all sorts of things if you know what you're doing. These are replacement parts. The one at the bottom, if you look up probably NASA wrench printed in space, you'll learn a little bit more about that. Basically, they made a design on Earth that they needed on the International Space Station, and they transmitted it up. So they don't need mechanical engineers, designers, specialists on location. You can transmit it to them. This is a parametric shape. Somebody got their math PhD for this. This is a generated, this is a calculus equation that generates this surface. Prototyping pieces, like we were talking about. These show, if you grab the slide here, you can see retraction errors, especially on the red object on the bottom left there, where I printed it too fast, and it basically left this kind of lacy pattern. Now, of course, you can do that on purpose if you want. But for most applications, that would be a flaw. You might want to look up if you're dealing with this and you're dealing if your objects are popping off the build plate or getting warping, corners are not sticking down, etc. Look at heating it. I recommend against spray adhesives around your moving and electronic parts, but some people do use them. You might try printing with a raft, which is what you see at the bottom right there. And then this is what supports look like. So we can't extrude plastic floating in the air, right? So it either has to be supported by other means, or we have to print supports that build up to it and then cut them off afterwards. So the two dinosaurs you see here, one has supports attached and one does not. Because no matter what orientation we print these, and remember we talked about orientation before, no matter what orientation we print them in, they still need supports because some things don't touch the ground. Okay, there we are. So we're back to that process. So there's post-processing in there, right, after printing that you might have sometimes where you have to cut off those supports. So between printing and redoing concept, you may have a mini inspection step right there. And of course, there's a point here where you're also in your design choosing the right material for you to print, whether it's prototyping quickly or whether it's the question of what you want your final product to look like. Because 3D printing may be a prototype or it may be your final product. And to contact me, there's how I can be reached right there. Answer any questions anytime about this stuff. I'm happy to share that information. I do work in the public teaching domain. So I'm happy to share.